to this video on identifying linear, quadratic, or exponential functions. By the end of this video, you should be able to identify a linear, quadratic, or exponential function from multiple representations. All right, so the three functions that we have talked about this year have been linear, quadratic, and exponential. So we are able to look at equations, graphs, or tables of values and look for patterns and that help us identify each of those as a linear function, a quadratic function, or as an exponential function. If we're looking at the equation, if it's going to be linear, the degree is going to be 1. Now remember, the word degree means the highest exponent. Okay, so this is the highest exponent will be 1 if the graph is going to be linear. For quadratic, the highest exponent will be 2. And for exponential, you're going to have the variable in the exponent. The x is in the exponent in exponential. Hopefully that will kind of help you remember that. So here's some examples. We have 3 lines here. Look at this x to the first. X to the first, x to the first. The highest degree is 1. That makes all of those linear. In these next examples, x squared, x squared, x squared. The highest exponent is a 2, so the degree is 2. That makes it quadratic. And then in our last one, notice we have variables in the exponents, and that makes it exponential. So let's kind of look at a couple of these examples and see if we're able to identify. In example number 1, the x is in the exponent. And remember, if the x is in the exponent, it's automatically exponential. Okay, let's look at number 2. Looking at number 2, I see an exponent of 2 and an exponent of 1, which means the degree is 2. The highest exponent is 2, which makes this a quadratic equation. Example 3, looking at that, I have an x to the first. That means the highest exponent is a 1, so it has a degree of 1, which makes this a linear equation. And in our last example, I'm looking at it and I notice that there's an x in the exponent. When you have an x in the exponent, it is exponential. All right, so that's how we are able to identify from an equation. Let us take a look at how to identify linear, quadratic, or exponential from a graph. So on here, notice they're still in the same columns. Linears are all the left-hand column, quadratics are all the middle column, and exponentials are all the right-hand column. If a graph makes a straight line, it's linear. There's really no other way to say that. If a graph is a quadratic, it's going to have a U-shaped graph that opens up or down, and the U-shaped graph is called a parabola. And for exponential, it's a little harder to describe, but essentially it's going to rise or fall quickly in one direction. So when we look at this graph, this is actually a decay because it gets smaller as it goes from left to right. It falls very rapidly going from left to right. Exponential growth would have been the other. It would have risen very quickly going from left to right. So let's try some examples here. Example 5. We've got a graph that falls very rapidly from left to right. This is going to be an exponential. Now they might give you a graph that's not actually looking like our traditional with all the cross marks. They might give you a scatter plot. Looking at the scatter plot, I can clearly see the shape in here. That looks an awful lot like that one. It falls very quickly going left to right. This is exponential also. All right, look at example 7. This is a straight line, and we said if the graph makes a straight line, it's linear. And we have this last graph here. Now this, you're thinking, well, we said linear, we said exponential, this must be quadratic. Remember, a quadratic is a U-shaped graph. That is not a U-shaped graph, that's a V-shaped graph. It has a point at the end. So this is actually none of them. Sometimes that will happen. You can have that as an option. So this is none. This is neither linear, quadratic, or exponential. Right? Let's finish these by flipping over. Now, how can we tell from a table of values? The table of values are the most interesting to me of all the ways to identify linear, quadratic, or exponential. The first thing you have to know is all the x values have to be have what they call a common difference. They're changing by the same amount every single time. Otherwise, these patterns won't work for us. Okay, and so what that means, usually we could be counting by ones. So all of our examples, all the x values are fine. They're always counting by 1. You could count by 5s or 10s or however your graph is necessary, but it'd have to be counting by the same amount each time. You can't have differing differences between your x values for these patterns to work. So for a table of values to be identified as linear, first thing we have to know is we'll never see the same y value twice. It just is not going to happen. And then there's something called the first differences are the same for the y values. Okay, so we're going to look at the differences between the y values and they'll all be the same, and that will be linear. And we'll make a little bit more sense in a minute. For quadratic, you could see the same y value more than once because a quadratic comes down and turns around and comes back up. So you could end up seeing the same y value more than one time. That's not a problem. And there's something called the second differences. In a quadratic, the second differences are the same for the y values. Okay, so we'll see what that looks like. And then in an exponential, the y value will change much quicker than the x value. So when you see something where the y values are changing much quicker than the x value, you want to look for a common ratio or the common multiplication pattern in the y's to see if it's exponential. And same with linear, you'll never see the same y value twice. Okay, but we're not listing all the y values, so you don't necessarily have that as something you can look back on. So let's look at the first one. We don't have to worry about the x's. I'm always counting by ones here, so we're okay. But what we want to do is we want to look at the differences in the y's. So when I look at from -2 to 1, and then 1 to 4, and 4 to 7, and 7 to 10, what I'm noticing pretty quickly is if I add 3 between each of these numbers, I get the next number. So really this could be an arithmetic sequence if we wanted. We could write it like that, but I checked the differences and they're all the same. This is called the first difference. This is the first time I checked them. They're all the same. So the first differences are the same, which makes this linear. And it's linear because the first differences are the same. Let's try it again and see what happens. So let's look at number 10. So to get from -6 to -6, I'd add 0 to it. So I'm just going to write I added 0. From -6 to -4, I added 2. -4 to 0, I had to add 4, and 0 to 6, I added 6. So the first time I checked the differences, they were not the same. So this is not linear. And when we look, we see the same y value twice, so it couldn't be linear or exponential. Okay? So as I continue to examine it, I got to remember there's something called a second difference. So let me take a look. To get from 0 to 2, I would add 2. To get from 2 to 4, I would also add 2. To get from 4 to 6, I would add 2 again. The second time I checked my differences, they were all the same. So that makes this a quadratic function. And it's quadratic because the second differences are the same. right, let's keep trying and see what we have here. We'll try number 11. So I see some decimals, and I'm trying to think, what would I add to 0.08 to get to 0.4? I could add 0.32. But if I add 0.32 here, I do not get 2. I get 0.72. That doesn't work. I'm going to cross that out to look at that. The other thing, I guess the second differences would be the same. Could be the same. But what I'm seeing that had me thinking, I noticed that maybe, I know that 2 times 5 is 10. And I just saw that and I was like, let me check this relationship. And so I'm going to try that again. So we're going to look at our calculators. And we're going to try and we're going to see what happens. Okay. So we're wondering, this 0.5 work times 5 worked 2 to 10. Is 0.4 times 5, is that 2? Ah, it is. Is 0.08 times 5 0.4? It is. So I've got a relationship here where I am multiplying by the same number each time. That's a common ratio. We just did those with exponential functions, so this is a common ratio. And if it has a common multiplication pattern, that makes it exponential. Okay, let's try it again. Practice helps us start to see patterns. All right, so let's take a look. First thing I always check is addition and subtraction. So to get from 5 to 4, I notice that would be a +1. 4 to 2 would be a +2. So right there, I already know this is not linear because my first differences are different. To get from 2 to 4, I would, this one changes to a -1. So we got to make a adjustment here on this one. So this number, it said -2, we're going to make it -1. Okay, so to get from 4 to -1, we got to add 3. From -1 to 4, we have to add 5. And from 4 to 11, we'd have to add 7. Clearly not. The first differences are not the same. Let me look at the second differences. To get from 1 to 3, I'd have to add 2. 3 to 5, I would add 2. 5 to 7, add 2. The second time I checked my differences, they were the same. So this is quadratic. All right, pause the video, try the last 2 on your own, and then come back and check when you're done. All right, in number 13, I added 4 between each of the terms. That means the first time I checked the differences, they were the same, so it's linear. And then in number 14, the first time I checked the differences, they were not the same. When I checked them again, I noticed that they were the same the second time, so that makes it quadratic. Hopefully that was helpful. Let me know if you have any questions, and I'll see you in class.